Hello students, it is lecture 3 of mathematical physics, and today we will solve some question of numerical integration, like a question of numerical integration, and then later on discuss other topics. So uh, root finding and integration, these are two, like finding roots and integration are two of the important topics under numerical method, which we already did. You can watch our previous videos for more information. So the question given today is integrate e raised to power minus x square dx with the limit 1 is to 5. Okay, we will solve this question using trapezoidal method. On going for analytical method, it might create a mess, like it's not that easy to solve it with analytical method. So we'll be using trapezoidal method, and trapezoidal method is a numerical method and it gives an approximate answer. Okay, so let us use trapezoidal method with the step size of 1. We're taking step size as 1, so h is equal to 1. Limit from 1 to 5, so x0 is 1, xn is 5. What is n? Xn minus x0 upon h, that is 4. It means x1 is here, x2 is here, 1 2 3 4. Okay, what are the value in between? That is 1 2 3 4. Okay, 1 2 3 4 and 5. Now as per the formula that we all know for trapezoidal method is I is equal to h by 2 into f0 plus fn plus 2 into f1 plus f2, that is all in between f1 f0 and fn. Okay, so what do we write here? I is equal to h by 2 into f0 plus f4, that is first and last, plus 2 into f1 plus f2 plus f3, as all three of them are in between. On putting out the values, like e raised to power minus 1 square plus e raised to power minus 5 square plus 2 into e raised to power minus 2 square minus 3 square minus 4 square. On solving this, we get e raised to power minus 1, e raised to power minus 25, e raised to power minus 4, minus 9 and minus 16. And on solving this, we take the value of e raised to power minus 25 as 0, like that's quite negligible, that's why we are taking it as 0. E raised to power minus 9 also 0, and e raised to power minus 16 also 0, because they are quite smaller number as compared to the rest. And what the answer we get here is 0.2015. Your answers can vary because it is an approximation method, and whatever we are just ignoring few numbers, and those few numbers might put some effect in your answer, so it may vary. But yeah, your approximate answer is 0.2015 using trapezoidal rule. Now in our earlier videos we discussed about the error topic, like which method we use for finding the roots and which one should be used and which one should not be used. We will be discussing error estimation in numerical integration, like if we are doing integration, which method should be used and which should not be, and which is more comfortable or which gives a better result. We will discuss the particular thing in this next part. So here it involves a lot of calculations, so be specific, be focused about the topics I'm writing, about the thing I'm writing, and kindly look out. If you have any query, any problem, do comment, and thank you. Yeah, so first we will solve the error estimation in the trapezoidal rule. Like first we will go for the trapezoidal rule. Generally we are taking an integral here. Okay, so we take the integral I is equal to small I to f, like initial limit to final limit fx dx. Okay, if we expand this fx about h by 2 using Taylor expansion, what do we get here is fx is equal to fh by 2, that is we should write it as fx naught plus Do you remember, like earlier we wrote it like fx0 and etc etc. So we are expanding it about h by 2. So what do we get here is fh by 2 plus plus x minus h by 2 f dash h by 2 plus 1 upon 2 factorial x minus h by 2 whole square f double dash h by 2 plus 1 upon 3 factorial x minus h by 2 cube h triple dash h by 2. Okay, and it continues so on. Now when we put x is equal to 0, the equation we get here, f0 is equal to fh by 2 minus h by 2 f dash h by 2 plus 1 upon 2 h square by h by h square by 4 f double dash h by 2 minus 1 upon 3 factorial h cube upon 8 f triple dash h by 2. See what we did here, we put 0 at the place of x. Okay, so when we put this term gets negative, the third term, that the fourth term gets negative. Okay, so in the first step we take fx, expand it about h by 2, and the next step we put the value of x is equal to 0. Now in the third step we put the value of x as h, like we are taking the step, like if it is an interval 0 and 1, this distance was h, right? H was the step size. So what we are doing here is taking the initial f0 and we are taking the one step, like we are taking h. Okay, so on putting the value of h in this particular equation 1, what we get here, fh by 2 plus h by 2 f dash h by 2 plus 1 upon 2 factorial h square upon 4 f double dash h by 2 plus 1 upon 3 factorial h cube by 8 f triple dash h by 2, and it continues later on. Now what we do here, we take h by 2 into f0 plus fh, which is area of trapezoid. Like it is f0, this distance is f0, this distance is fh, okay, and this is the h, which is step size, and 1 upon 2. What is the area of trapezium? 1 upon 2 into sum of parallel sides into height, that is 1 upon 2 sum of parallel sides at f0 plus fh into h, that is the height, which is area of trapezium. So from the above two equation, when we add it and multiply it by h by 2, the result we get here is h into fh by 2 plus h cube by 8 f double dash h by 2. Thing to notice here is this term and this term get cancels out, this term and this term do get cancel out. Okay, the plus and the minus term cancel out each other. What we have here is given here. Okay, I hope this thing is pretty clear to you all. If there is any query, any problem, any calculation error, kindly mention it. Okay, there can be some inaccuracy, there can be some issues, so please mention it. It's all numerical part, it's all calculation thing, so there can be some issue. Now what do? We integrate 0 to h f dash x dx, like we are integrating this function from 0 to h. Okay, how do you integrate it? Like 0 to h f dash x dx, and as we wrote here fx, we will be integrating it from 0 to h with dx. Okay, so what we get here, h fh by 2, we are writing fh by 2 as it is because it is a constant. This integration is not putting any effect on it. fh by 2, f dash h by 2, and everything is a constant value. It is not dependent on x. Okay, hence we are writing it as it is. So the next thing we do here is hf h by 2 plus f dash h by 2 integral 0 to h x minus h by 2 dx plus 1 upon 2 f double dash h by 2 0 to integral x minus h by 2 whole square dx plus f triple dash h by 2 upon 3 factorial 0 to h x minus h by 2 raised to power 3 dx. What we did here is nothing. We are just integrating the equation 1 we wrote earlier. Okay. Now we change this part of bracket equal to x. We take it as equal to s. Okay, x minus h by 2 is equal to s, then dx is equal to ds, the rest of the term is constant. Now changing the limits, x is equal to 0, then s is equal to minus h by 2. When x is equal to h, then s is equal to h by 2. Okay, so what will be the limit of the new part? It will be from minus h by 2 to plus h by 2. Okay, now we write the same part with changed version, like h by 2 will remain the same, like there is no limit or nothing integral function applied to it, but in the next part we write as minus h by 2 to h by 2 s ds f dash h by 2. F dash h by 2 is as it is because it is a constant term, it is not having dependency on x, plus 1 upon 2 f double dash h by 2, an integral from minus h by 2 to plus h by 2 s square ds. Okay, 1 upon 3 factorial f triple dash h by 3 integral from minus h by 2 to plus h by 2 s cube ds. Okay, so we write it as in and find out the values of it. Like on solving it, what we get, h f h by 2 plus h cube upon 24 f double dash h by 2 plus h cube, so yeah, it's h cube by 24 f double dash h by 2 plus h5, like h raised to power 5 upon 4 factorial 80 f like derivative of 4 times like f4 dash h by 2. Here was some of the like calculation error I made. I wrote it here 3 only, it was 5. Okay, now when we move from this step to this step, the thing that has happened here, minus h by 2 to plus h by 2 s ds, it is an odd function, removed. Like integral of an odd function from minus like it is an identity in integral, right? And its value is 0 for odd function. Yeah, it is 0. So all odd functions are removed, like their value is 0. So I'm multiplying this thing with 0, we neglect them. So what we remain, like what we get remaining in the function is this part, the second and the fourth one. Okay, so we move ahead. We mark this equation as equation 5. Okay, and we have marked this equation as equation 4. What this equation was, the area of trapezium. What this equation is, the integral of that particular function. Okay, now equation 5 minus equation 4, this integral minus the area of trapezium. What the area of trapezium was giving to us, area of trapezium was a method for us to integrate, right? So whatever the difference will be an error. Okay, and this error will be for 0 to h range, like cause we have considered the interval 0 to h, correct? So IH minus h by 2 f naught plus fh gives out the term that is making an error here is h cube upon 24. Sorry, this thing will get subtracted from this thing, and whatever error we will get here is minus h cube upon 12 f double dash h by 2. Okay, there so like I was saying, this thing, this term minus h cube upon 12 f double dash h by 2 has other terms too, but they are quite small, so we are not considering them, like we are leaving them out. Okay, so what we get here, IH is equal to h by 2 f dot like f0 plus fh minus h cube upon 12 f double dash h by 2. What do we call this term? We call it as local error. Local error because whatever we did for the integral was for the interval 0 to h, but there are multiple of spaces, like, okay, there are n intervals, right? And what we did it for 1. We cannot simply multiply it by n, because it's not confirmed that every time you will be getting same thing, okay, like same curve, okay. So for this particular function, as shown here, integral is equal to integral, that is summation in, okay, in as in signifying each part as I1, I2, I3, I4, like that. I is equal to h by 2 f0 plus fn plus 2 f1, f2, f3 dash 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 etc. minus this thing. Like how this came now? In this equation, when we put the values one by one, like I1 plus I2 plus I3 plus I4 plus I5, what do we get here is, like, the first term remains 1, the last term remains 1, rest all terms are repeated, like 0 1 1 2 3 4 4 5 5 6 6 7. You getting it? Like whatever be the values, the excluding the last and the first term, everything will be repeated, like it will be said twice, okay. So what we write here, h by 2 f0 plus fn, that is the first and the last term, plus 2 into f1 plus f2 and whatever comes in between, minus h cube, which was the other thing, h cube by 12 as it is, f double dash x naught or xn. Like we are taking error, like f double dash at either x naught, that is the first term, or xn, checking out which of them give the maximum value, okay. And we, as we go for the maximum thing, okay, like we will be finding out f double dash x naught, f double dash xn, and whatever gives the maximum value, we will be using that, and n, because it is used n times, okay. And this particular thing is called global error, okay. And here it is mentioned h cube by 12 n modulus of f double dash x naught or xn, okay. And as we all know, h can be written in terms of n and n can be written in terms of h, as n is equal to xn by x naught upon h, okay. So we replace here this thing, and at the place of n we will be writing xn minus x naught upon h, and we reduce this h with the upper one, and what we get here, x naught xn minus x naught h square upon 12 f double dash x naught or xn. It is second order error, like it gives the error of order 2. Now if we eliminate f double dash n by 2 from equation 6 using 5, like then replace h by 2h, then we can get Simpson rule formula. Like it is saying this thing, okay, it is equation 6, okay. When we, like, yeah, it is equation 6 given here, okay. Now when we remove f double dash term, this term from this equation, using the fifth equation, okay, using this equation, like multiplying it by 2 and subtracting it from that term, and so now we replace h by 2h, then what we can obtain is the Simpson rule, and error in Simpson rule is xn by x naught as same, h raised to power 4 f 4 times of it, like fourth derivative x naught xn divided by 180. Okay, we will discuss this thing later on, how this all came. Like, as as we have mentioned earlier, like you need to subtract them, multiplying by 2, subtract them and replacing h by 2h. We obtain this rule, we obtain the error for it. Okay, and the thing about Simpson rule is it gives an fourth order error. Like, it's more clear, more accurate answer with the Simpson thing, so you better use this one. Okay, I hope this part is clear to you. It involved a lot of calculation stuff, so you need to be, apt and attentive towards it, like what exactly thing is going on. The next topic is interpolation or extrapolation. Okay, so when the value of function at different point is given and value at some other point is to be found, then we use interpolation technique. Okay, for example, we are giving you an observation, like this happened at this and this happened at this and this particular thing is happening at this. Now tell me what will happen at an observation in between. That is the scenario where we use interpolation. Okay, interpolation techniques. And one thing we need to know, if n plus 1 data points are given, we can fit a nth order polynomial through these. Okay, for example, there are 3 points given, we can make a 2 order polynomial. Okay, if there are 5 points given, we can make a 4th order polynomial relation for those points. It is a rule. Okay, if there are n plus 1 data points, then the polynomial equation can be of n order. Okay, so here we go through it. Let fx is equal to and one thing, it also involves a lot of matrix work, a lot of calculations, so you be attentive. The only thing you need to remember is the formula. Okay, formulas are important. We will be discussing some part of theory later on too, but be specific about the formula thing. So let fx is equal to a0 plus a1x plus a2x square dash dash a n xn be a let fx is basically a polynomial which fits the given data points. Like, these are the data points and we made just a polynomial out of it. So we write this data as given data x0 xn. So f0 is equal to a0 plus a1 x0 plus a2 x0 square plus a3 x0 cube dash 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 a n x0 raised to power n. Similarly for f1, for f2, for f3, and we write it for fn, like a0 plus a1 xn plus a2 x2 square, a2 xn square plus a3 xn cube, and so on, so on, so on, and at the end we write as a n xn raised to power n. So we write this in the form of matrix as f0, f1, f2, fn is equal to this another matrix 1 x0, x0 square, x0 cube, x0 n, x1 square, x2 square, x1 square, x1 cube, x1 raised to power 4, x1 raised to power 5, x1 raised to power n, and similarly 1 xn, xn square, xn cube, xn raised to power n, and another column that is a0, a1, a2 da, 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 and an. Okay, so from this equation what we do, we try to find out the values of this particular these what do we call them, constant or a0, a1, a2 and all. So we take inverse of this, and what we get here is this column matrix a0, a1, a2, a4, a5, an is equal to this whole thing inverse f0, f1, f2 dash 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 fn. This particular thing is basically the equation which gives the coefficients. Okay, and this provide a basic method for interpolation. This is the method for interpolation. Okay, what we get here is like this particular method will give out the value of the coefficient, and once we know the coefficient we get the equation, and once we get the equation we can find out the value. Okay, now there are various methods under interpolation, and what we next discuss is Lagrangian interpolation formula. Okay, so here we discuss the Lagrangian interpolation formula. Under this, let 3 points are given to us: x0, x1, x2, f0, f1, f2. Now when we write polynomial through these data points, what we write as px is equal to a naught x minus x1 x minus x2 plus a1 x minus x naught x minus x2 and a3 x minus x naught x minus x1. Something special about this particular polynomial is k, like we are writing x0 term, so we'll be skipping the x0 term here. We are writing a1 term, we'll be skipping the x1 term here. We are writing a3 here, we'll be skipping the x3 term into further multiplication. Okay, now when we put like find out a0, when we find out a0 as in like at the place of px when it is f0, okay, so we replace this x by x0. So what we get here is a0 is equal to f0 divided by x0 minus x1 and x0 minus x2. Okay, if we look out at other terms, the thing of choosing this particular type of polynomial was k. If we would have chosen some other numbers, like for a1, if we would have chosen a1 like x1 here, it would not have turned to 0. Okay, so but we are taking this particular type of format so that whenever we take one value, the rest of those terms get 0. Like the value I will take for this one will make the other 0, the value I will take for this one will make the other 0, and the value I will take for this one will make the other 0 too. Okay, for example, we are taking at x as x0, then these two will turn 0, like x0 minus x0 will be cancelled out, x0 minus x0 will be cancelled out. For the next one, if we are taking x1, this term will cancel out, this term will cancel out, we will remain like we will get this term. If we are taking out x2, we are taking as x2. Okay, these two terms, this one and this one will be cancelled out. What we'll get here is this one. So a0 is equal to f0 upon x0 minus x1 x0 minus x2. Remember, what we are doing here is taking value of x. Okay, we are taking the value of x as x0, x1 and x2, and we are finding out these a1, a0 and a2, and with the help of these we put this value in the polynomial given, and this is the Lagrangian interpolation polynomial for 3 data points. It is the formula for Lagrangian interpolation polynomial for 3 data points. See, what we did here was just taking out the layout. What we did here is taking the layout of this particular polynomial, that's it. We did nothing, we just shifted the terms, and what we got here is the px function, that is a polynomial function for the given data points. Now for n plus 1 data points, that was for like 3 data points. For n plus 1 data points, what we write here as this is the observation x0, f0, x1, x1, xn, fn. Px, that is a polynomial, is equal to sigma I is equal to 0 to n fi ci. Okay, and ci is defined as pi. Pi is for product and sigma is for sum. I hope you all are aware of it. Okay, so pi j such that I is not equal to j, x minus xj upon xi minus xj. Okay, it is the general formula for Lagrangian method for interpolation. Okay, the next is Newton interpolation formula. Today we will just discuss about the formula of Newton interpolation formula. In the later videos we will be discussing the theory related to it. Newton interpolation formula has two parts, the forward difference formula and backward difference formula. The forward difference formula is Px, that is the layout of the polynomial, as f0 plus s del f naught 1 factorial s minus 1 del square f naught 2 factorial plus s minus 1 s minus 2 upon 3 factorial del cube f0 and continues. What s here is x minus x naught upon h, okay, which is basically the interval. One thing that wherever we use Newton interpolation formula, the interval should be same, like x1 minus x0 should be equal to x2 minus x1 should be equal to x3 minus x2. This interval should be same, or uniform interval should be given here. So we got to know what s is. Like, now what is this del f naught? Suppose this is the observation we are taking: x0, x1, x2, x3, x4, x5, f0, f1, f2, da 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 da. Okay, now whatever the difference will be between f1 and f0 will be called as del f0. Okay, difference between f2 and f1, del f1. Difference between f3 and f2 is del f2. Difference between f4 and f3 is del f3, and difference between f5 and f4 is del f4. Okay, next, del square f. Whatever the difference will be between del f1 and del f0 will be written as del square f0. Whatever the difference will be between del f2 and del f1 will be del square f2. Del square f1. Difference between del f3 minus and del f2 will be del square f2, and difference between del f4 minus del f3 will be del square f3. And similarly we will take del cube f. See, all we are doing is just subtracting the lower to the upper one. Like, del square f1 minus del square f0 is del cube f0. Del square f2 minus del square f1 is del cube fn, and del square f3 minus del square f2 gives out del cube f2. And similarly we continue it. Del raised to power 4 f is del 4, like del 3 f1 minus del 3 f0 is del 4 f0, and del 3 f2 minus del 3 f1 is del f1, del 4 f1, and on subtracting them what we get here, del 5 f0. So whatever the del thing written in this Newton interpolation forward difference formula was mentioned, it was just a difference of the previous cube. Okay, now as the forward difference formula is clear to you all, now we will write down the backward difference formula and discuss what are the values in this particular formula. The backward difference formula is, the thing about backward difference formula is it starts from the end. Okay, in the forward difference formula we began with f0, but here we are beginning with px is equal to fn, okay, s del fn by 1. See, earlier what we used to do was writing del f0, del square f0, del square f5, but what we will do here is we begin from the end. Like, for example, for this observation, this last observation is fn. Okay, so we see the formula again: fn plus s del fn upon 1 factorial plus s into s plus 1. Earlier what we used to do was subtract 1. subtract 2, subtract 3, but here what we'll be doing is adding one. S into s plus 1 del square fn upon 2 factorial plus s into s plus 1 into s plus 2 upon 3 factorial del cube fn, and continues. Okay, what this del this time here is these lower values. Okay, as I'm saying it, this is fn, like this is fn, this is del fn, this thing will be del square fn, this thing will be del cube fn, this thing will be del 4 fn, this thing will be del 5 fn. Okay, what it will go in the order is, it goes in the reverse order. Okay, earlier we are going from top to bottom, but this time it will go from bottom to top. So we will be discussing this in the next video. We will be discussing solving questions with the particular method. Okay, and s here is x minus xn upon h, or sorry, n. Okay, we will be discussing it. Earlier we used to take like x minus x naught, but this time it is x minus xn upon n, or sorry, h. H is the interval between the data points, and we will solve questions in the next video. It was a lot of numerical work today, like not mathematical, not numerical exactly, but a lot of things we did today. So for any of the query, do comment and check out. If you have any problem, do mention. Thank you.